Welcome to the August 2022 Raleigh Astronomy Club indoor meeting. Welcome first-time guests and new club members. So please be respectful during the presentation and hold your questions until the end, unless the speakers ask for questions while speaking. If you're on Zoom, welcome. Thank you for joining. If you could use the chat feature in Zoom, queue up your questions there. We will take a break, definitely have time at the end, and we'll read them out for everybody to hear. When asking the question, we ask if you speak into a microphone. We have one that we'll pass around so that everybody can hear the question and it gets recorded. All right, so tonight we are joined by Ken Brandt and Doug Ellison. Ken is the director of the Robeson Planetarium and Science Center in Lumberton, North Carolina, and is a NASA JPL Solar System Ambassador. He's a U.S. Navy veteran, a former high school teacher, and nationally board certified. In addition to his duties at the Planetarium, he's also an astronomy lecturer at USC Beaufort. Doug received his BS in Multimedia Design from Montfort University in Leicester, England in 2001. Hopefully I pronounced that correctly. He joined NASA's Jet Propulsion Lab in 2010 to work on data visualization projects for education and public outreach before joining the Mars Science Laboratory team in 2016 as part of the Engineering Camera Payload Uplink team. As well as operating the engineering cameras on the Opportunity rover, he became the engineering camera team lead in 2019 and the Curiosity Integrated Planning and Execution team chief in January of this year, 2022. And he has commanded the acquisition of more than 18,000 pictures from Mars. Today's topic is Curiosity's 10th anniversary. Plodding ever onward, NASA's Curiosity rover has overcome the difficulties of getting to Mars, battled 7 minutes of landing terror, endured brutal Martian elements, and improvised fixes in the face of impending equipment failure to deliver awe-inspiring images and scientific results. Tonight, Ken and Doug are joining us to celebrate 10 years of scientific discovery and innovation from the Curiosity rover.
Good evening, everybody. I'll start things off here. Basically, we're going to be talking about the introductory stuff and talk about where Curiosity had gotten to by the time of the pandemic. So we go from, thinking about, hey, maybe we should send a rover to Mars, to as everything was shutting down and everybody was going home. Now you want to keep track of that email address you see down there, because I have these. These are Mars One team stickers. I don't know if they're valuable now, but I have a feeling they will be someday. So I'm going to give you a couple seconds to jot that down and take a pic or whatever, because I'm also available to talk to you as a solar system ambassador. My job is to give lectures about these things and talk about them and do fun things with kids and all that other thing. But you can always come down to my planetarium. Now, right now it's an inflatable, but in 3 years we will have the real deal. Anyway, next slide. Whoops. Okay, that didn't. Oh, sorry, Doug. That's right. You're doing that. There's the Earth. And there's Mars. Now, the most striking thing about this slide, when you really look at and take it down to individual figures in the graph here, the chart, you'll notice the surface area, land surface area of both planets is pretty close to one another. All the rest of the numbers, except for the length of day, that's relatively close. But the temperature range isn't as bad as I thought it was. Let's see what this other one is. Oh yeah, atmospheric pressure is a lot lower on Mars. Okay, next slide, please. So this is the Mars surface mission family portrait of successful missions. If you look across the globe of Mars stretched out there in a Mercator projection, I guess, you're seeing that Phoenix only landed slightly north of where Viking 2 landed. I find that interesting. So Viking 2 is sort of an Arctic Circle explorer on Mars 30 years before Phoenix did it. So that I always found interesting. But this is a very cool graph. It shows everybody that's played the game and won the game of getting to Mars and working successfully. Next slide, please. All right, scale model time. You're seeing the two engineers there, or scientists, I'm not sure which. They're talking in the Mars yard at JPL, which is where they test out, JPL's engineers and scientists test out all the different surfaces as they encounter them on Mars. You'll notice behind their heads there was a hill made out of cobblestones, basically, that Opportunity climbed. I think that's Opportunity, right, Doug? Or Spirit?
This one right here is the test bed of both rovers.
Okay. All right. So yeah, you see the Opportunity and Spirit rovers there to the left of the people talking there. And to the right, of course, Curiosity and the slightly larger version of that, Perseverance. And of course,
just one second, Ken. I think they might be having difficulty in the room. Looking at the presenter cam, it seems like we've been shrunk to the size of a first class stamp in the top left corner.
We're trying to get it back here.
Okay, we'll give you a minute or two to try and figure it out. While they're figuring it out, I'll let people know. So these are all essentially engineering copies of the flight vehicles. This is Marie Curie, which is a copy of Sojourner. This was nicknamed Dusty, which is a copy of Spirit and Opportunity. And then this is called Maggie, which is the stunt double of Curiosity. And we do now have a copy of Perseverance as well. Marie Curie and Dusty now live in the Air and Space Museum. And one day, perhaps, we will park Maggie there as well.
And believe it or not, the Robeson Planetarium actually held another full-scale model of Opportunity. They named that one Marvin. And I'm pretty sure that stays in the Mars control room, right? I know it was somewhere on campus when John Callis is running.
It used to. Okay, Ken, we're back full screen. Back to you.
Well, let's roll. Next slide, please. And that's where Opportunity ended up, in this in the rim of Endeavour crater at Perseverance Cove. How significant. Well, they didn't know at the time, Perseverance was going to be the name of a new Mars rover in a couple of years. So that's pretty cool. But this represents a 20, next slide, I'm sorry. This represents 28 miles of driving on Mars right there. And you can see length of the time they were there. I love to compare Opportunity's lifespan to a human being's lifespan, and a human being running, basically 40, whatever the math is, darn it, 49 something sols past its warranty. It was only supposed to last 90 days. And 5,000 sols later almost, it conked out finally because of a Martian dust storm. And the solar panels, what everybody always thought would be the fatal flaw, was finally the fatal flaw. But you would live to be 4,000 and something years if you're running on Opportunity's timeline. So these other rovers are cool and I like them a lot, but Opportunity is still my baby. It's my favorite. Okay, next slide, please. And this is one of the reasons, because Opportunity's mission and PR was very much directed at let these people follow what we're doing on Mars for both Spirit and Opportunity. And I always joke with my students, I said, look, if you get up and you get to your computer before 11 a.m., you're seeing the stuff from Mars before the engineers and the scientists are showing up to work in California. And so I said, that's pretty cool. You can actually see Mars before they do. And they're the ones that ordered up the pictures. So, I always thought that was pretty cool. And of course, Opportunity and Spirit both took us all for a really, really cool ride among Mars. Next slide, please. And of course, happy 10th anniversary of Curiosity. The link down there is supposed to link to a happy birthday thing played with the same instrument. And Doug, can you tell them a little bit about that story and about what's happening now?
Yeah, so one of the instruments inside Curiosity is called SAM. It stands for Sample Analysis at Mars, and we drop something about the size of a baby aspirin in terms of drilled rock samples into it, and it gets vibrated down a funnel into little cups for analysis. And the piezoelectric vibration can actually be tuned. And some of the engineers on the SAM team thought it would be appropriate when on its first birthday, they programmed the SAM instrument to use that piezoelectric vibration to actually play Happy Birthday to itself, which at face value is very cool and exciting. But then if you imagine standing right next to Curiosity, you've got this rover all alone, 100 million miles in every direction, quietly sat there singing Happy Birthday to itself with no cake, no candles, and no one to share them with. So fast forward 9 more years, and what's adorable is the Husqvarna company, who make robotic lawnmowers, programmed all of their robotic lawnmowers to sing Happy Birthday on Curiosity's 10th birthday with shameless marketing campaign, but the notion that no robot should have to sing Happy Birthday to itself, which we all thought was absolutely adorable.
Very, very good. Thank you. Next slide, please. So Curiosity's goal there, you can see what the 4 dots are there. Could it have supported life in the past? Does the geology and geochemistry support the story of water that everybody thought was happening in Gale Crater? Of course, measuring different levels of gases, to include methane, by the way, as it was traversing over Mars. And of course, radiation levels and hazards. Perseverance is also doing this. So we're gathering a pretty good picture of what the hazards are for astronauts on Mars. And you have to remember, both of these spacecraft are fairly low down they landed fairly low down on the surface of Mars. I think it's negative 2.5 kilometers from what would be mean sea level. Is that right?
Something like that. Yeah, I think about 4.3 K below Martian sea level, basically.
Right. Okay. So maybe I had it in miles. Sorry. Next slide, please. Now, let's go back to that previous slide for a minute. Just to have a look. That was then. Fast forward. Next slide. This is now. This is after about 9.5 years of driving around on Mars. This thing looks really, really dirty. And, one of the things they have to do is work really hard so that when they get samples from a different location on Mars, this dust doesn't interfere with the findings from those samples. So there's a lot of what are they, airlocks or something like that on top at the entrance bays for each of the instruments. Yeah, those. Next slide, please. And that's where she landed. The ellipse is much, much smaller when Perseverance landed 10 years later, or almost 10 years later. That ellipse was shrunk down to about 1/3 of that size, maybe more. But that meant that opened up a whole lot other range of potential landing sites, because now you can get even more accurate in your descent and landing. So they could land in a place like Jezero Crater. But this one, and Doug, to be very honest, I forgot what the blue box was.
The blue box is what we're about to look at in the next slide.
Okay, right. So next slide, please. Oh, yeah. Of all of these landmarks along the way, I think my favorite happens to be the blue one up there at the top, Bradbury Landing. Ray Bradbury had just passed on when Curiosity landed on Mars, and the mission team thought it was appropriate to name the landing site for him, which I thought was pretty cool. Nice way to commemorate a life well lived and well written. But you can see all these different points where you probably have heard some of these before, like Pahrump, the Pahrump Hills, or one of my favorites, Old Soaker. Okay, I love that. Doug, I'd love to hear the story with Old Soaker.
So what's a little hard to pick apart with a map like this, but we have a version of a map that is the entire landing area sliced into about 1 mile boxes, each of which was mapped by a different member of our science team. And the privilege they got of having mapped it was to give it a name. And so we have a Glen Torridon quadrant and a Death Valley quadrant and the Kimberley quadrant, which is in Australia. And all of the things within that quadrant get named after the geographic location of that particular name. So we've been naming for 4 years or so, we've been naming almost everything after Scottish places because we've been exploring an area we've called Glen Torridon. The Old Soka, I'm not sure which quadrant we were in at the time, but Old Soka was a geological formation somewhere on Earth that we then named a rock that we found that we actually drove past. And only after the scientists had a chance to look at the images more closely, they realized it had these tiny, tiny little fractures in it. We turned around, went back, and took a closer look because those fractures were actually desiccation cracks. They were the leftover symptoms of that forming as a mudstone as a lake or a river evaporated away, and hence the name Old Soka, because at one point that particular rock was just soaking wet mud that later went on to form rock.
Very cool. Please put the next slide up. Thank you. So these are the different geological units that Curiosity is traversing on its way up the hill there. And if I'm remembering what I saw yesterday, right, or the other day, the hill's at the very top to the left of the word mission. Curiosity couldn't go through those. Is that right, Doug?
Yeah, I have a slide that shows just how far we ever expect to get, and basically it is to the very beginning of these crazy bright rocks here, but certainly not into them or beyond for sure.
I'm sorry, didn't mean to steal your thunder. Next slide, please. So here we have evidence of a lake bed, a river delta, various rivers flowing down into that lake and delta, and of course the lake floor itself. So this is another really good place. If you're a fossil hunter, this is a really good place to go looking. Problem is there's no way to get the samples from here back to Earth. We will be able to get rock samples back from Perseverance in about, 10 years? And those samples will tell us a lot. Now, I remember mentioning prizes here, and I'll go ahead and ask what question now and see if I get a winner. The question is, on what date does Mars reach opposition? Somebody put a hand up, somebody in the room call on them, and we'll see what happens. Uh-oh, I hear crickets. No. Anybody? Going once?
Well, I've got the microphone, so.
Oh, go ahead, Naveen.
What'd you say, Steve? Sometime in December.
Sometime in December is going to have to do. That works. So, Steve, what you need to do is email me, and I'll send you one of these Mars One stickers by mail. Okay? Because I don't, I can't fax them to you or whatever. Okay, so next slide, please. It was December 2nd, I believe, by the way. Oh, look at all those pretty holes. Those are drill holes. And the thing I like to show my students whenever I show a slide like this is how Mars is that kind of burnt orange color in the fourth hole down on the left. And a lot of what comes out of Mars is nothing like that color, like all the grays and bluish and even greenish rocks that come out of the drill hole. So that shows you very clearly why you need a drill, because you want to get down underneath that rust crust, to get at the rocks underneath. And, I remember somebody saying something about the Phoenix landing. You could grow broccoli in that soil, whereas with Opportunity, you kind of had to stick with tomatoes and, nurture the soil down a lot. But you could grow broccoli up there where Phoenix was, of course, avoiding the perchlorates. And Doug, what about perchlorate? How big of a deal is that for us for now and the future?
It's not great. If you take the bare constituents of a Mars soil, you kind of have to wash it first before you could use it. And in doing so, of course, you'd be washing away some of the bad stuff, like some of the perchlorates, but also some of the good stuff as well. And so you could use it as a medium in which to grow things for sure, but you'd need to kind of wash it first and then add nutrients back in again. But it's not entirely useless. In fact, there is a common commodity product used around the agency and elsewhere that is run by the guys at Johnson. They have essentially a Mars simulant that is a very, very crude approximation of Mars soil, and it is basically scooped off the side of Mauna Kea. It is volcanic sand from Mauna Kea.
Yeah, very cool. Now, if you want to do this at home, you can take a Brillo pad or a steel wool pad, get it wet, put it in the sun, leave it there for like 5 days, and then go back and get it. Okay, and it will look a whole lot like number 4 on the left there. Okay, fourth one down on the left. Because that's essentially, for the most part, what Mars soil is made out of: iron minerals that oxidize in the presence of a long time, just sitting around on the surface. Next slide, please. So yeah, Curiosity figured out that Mars is capable of supporting life, and you see this, what looks like to me a gas chromatograph of the constituents of the clay there, and it harkens me back to Viking. About 20 years ago, I learned this summer that a particular scientist had published a paper about the gas chromatograph on Vikings 1 and 2. And they made the suggestion that it was never designed to detect the kind of organics that are here. And so it basically returned a false negative for organics. And of course, when you go to interrogate the rest of the science experiments, well, yeah, there's no life there. It's a chemical reaction, a circadian chemical reaction, but I'm not going to talk any more about that. So this is the constituents. You can see all the goodies that make up proteins in that soil sample right there. You got water, of course, you got hydrogen, carbon dioxide, oxygen, sulfur dioxide, hydrogen sulfide. You mush all that together, you have the chemicals necessary for life. The other thing you need, of course, is opportunity and time. But we know that both of those exist now, don't we? Next slide, please. So here's more chlorine compounds in the soil. You can see some of them are kind of down below the reliability of the instrument, except for where Cumberland Gap is. Cumberland Gap shows a spike of these. And, Doug, do you guys have any more insight as to why that was?
So the situation you have is that very close to the surface, even embedded into a rock, the UV radiation is trying to break stuff down almost constantly. And so with the Cumberland Ridge location, what you've got is actually an eroding front. And so where we were drilling had not been exposed to the surface for billions of years. It was, geologically speaking, comparatively freshly exposed. And so we were just coming along and finishing the job of just going just a little bit deeper, and in doing so found that there were plenty of organics locked up in there. And so you need Mars to kind of help out as well, to have done its part in looking after those samples, so we can come along and take a look at them.
Next slide, please. Thank you. All right, well, you guys can read the slide here. Basically, the more complex an organic compound is, the more likely you can start to look at life as a possible reason for that. Does that say there's life on Mars? Not yet. I liken this to a murder mystery where the only thing you don't have is the body. Okay, until you find the body, literally the living things or their fossils, you can't say a thing. You can say, oh yeah, methane levels spike in the spring. That's cool. We saw all these organics here. That's cool. We have a delta. It's got the same organics across the other side of Mars. That's great. But you can't say you got life, because extraordinary claims require extraordinary evidence. Okay, next sticker. Who said that? Extraordinary claims. I see a hand up in the very front row over here in the white shirt. Yeah, man.
Carl Sagan.
Ding, 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 winner. Get my email and send me that Send me an address I can send the sticker to. You've won a Mars One commemorative sticker. I've got one more that I'm going to give away tonight. And Doug, you're already on the inside track to get a sticker, by the way. I got you one right here if you want it. I'll go ahead and go to the next slide, please. Oh, that's so beautiful. That is such a pretty picture. All right, so that circle, Doug, is what? That's where it is now?
Yeah, so I just wanted people to, and I'll highlight this so no one can be doubt about this. This little black dot right in the middle of this yellow circle.
Wow.
Just remember that little black dot, because I'm going to talk about it in a few minutes' time.
Very cool. Next slide, please, sir. All right, and this is where I turn things over to Doug Ellison, one of the crew chiefs for the Curiosity rover from the Jet Propulsion Lab.
So thank you, Ken. And good evening, everybody. It's a pleasure to be speaking to you this evening. And I am just one of a very large team of engineers, largely at the Jet Propulsion Lab here in Pasadena, California, but also a pretty large science team that's actually international. We have several hundred science team members involved in our mission. And as you can imagine, things changed dramatically 2.5 years ago. And we put this picture out when that happened to tell the story, the fact that we were now operating our Mars rover ever so slightly more remotely, just a little bit more remotely than we had been before, but doing it from our homes. What I like, if you look closely at the top left team member there, that's Kerry, who is our deputy rover planning team lead. Her cat, if you look closely, is actually trying to play with her mouse right there. Fortunately, we've not had a cat successfully send any commands to Curiosity yet. Camden, top right, he was also a rover planner. He's now with the Perseverance team. He'd had to set up on his dining room table. Carrie is our science operations team chief, bottom left. She runs a lot of our science operations for us. And Jack is the assistant planning team chief. He and I work together, keeping the planning team in running order. The transition to remote operations was quick. It was sudden. But I will credit my predecessor, Alicia Olbar, who ran the planning team before me, on trying to get ahead of the curve. We could all see what was happening coming down the road. And so the Thursday before JPL forced mandatory remote work, we actually all stayed home and essentially practiced a planning shift. We did what we called the ROUT, the Remote Operations User Thread Test. And it actually worked okay. What we were basically doing was all from home, remoting back into the exact same workstations we would have been using before, but doing it from home, and then using WebEx for our calls, for talking about stuff, and our meetings throughout the planning day. And that was the Thursday. The Monday, the lab shut. And we took Wednesday just to make sure we had everything in order. And that Friday, so only 4 days after the lab had shut, we actually did a nominal planning day where we actually had drilling, which is the most complicated thing the rover can do, is drilling. It's the toughest thing we do. It's the most involved thing we do. And we did that on our very first remote day of operations. Since then, the 2.5 years since we went remote, we have driven further. We have done more measurements. We have drilled more than the previous 7.5 years. We have had an incredibly productive time. Some of it is just the fortune of where we have been during these 2.5 years with the rover. Some of it is genuinely the creativity and the ingenuity of our team being able to do their job from wherever they need to. And we took those lessons learned and we actually put them into a paper. If you just Google for Commanding Curiosity from the Couch, you can find it. We did a report to the IEEE conference in Big Sky, but of course, it was remote. And you can download the PDF from the JPL Tech Report server or the NASA Tech Report server on exactly what that transition to remote operations was like, how it happened, how things have been going ever since. And I'll be honest, we are actually not requiring people, even though the lab is back open, and about 1/2 to 2/3 of the lab population is back on lab on any given day. We are not requiring our team to go back on lab. We are perfectly happy doing a complete hybrid. So some people go on lab to do their shifts. Some people stay at home and do their shifts. I was on shift as a super tactical uplink lead today. I happen to do it from right in this chair at home, about 11 miles from JPL. But the lessons learned we passed on to the world through this paper that anyone can download and enjoy. This is the larger team. You may notice that this was a team photo taken in 2018, 2019, because we've not been able to take a team photo like this since. And it's one of our first things we want to try and do when enough people are comfortable to come back is to take another team photo. Of the people in this photo, about a third have actually left the project, most of whom moved on to the Perseverance mission or Psyche or Europa Clipper, other exciting missions that we've got coming down the pipe in the not too distant future. And the people who've replaced them are, typically speaking, fresh college graduates. They're much, much younger team members, and they've done an incredible job of stepping up, taking the reins, and keeping our vehicle happy and healthy and productive. One person in particular who's not in this photo because she wasn't even at JPL at the time. I used to run the engineering camera team on Curiosity, and when I moved over to become the planning team chief, I took someone who was 2 years out of college and made her the engineering camera team lead, and she's doing an outstanding job on running our little team of engineering camera operators. But I'm just one person out of what is a very large team, and I'm very, very proud to be a part of what is an incredible, incredible project. So Ken talked about kind of earlier mission stuff, those early big achievements. What I'm going to talk about is those last 2.5 years. Those last 2.5 years, and let me turn on the laser pointer mode, those last 2.5 years are all down here. They're all in this kind of bottom fifth of this route. We've covered, as of this morning, 28.835 kilometers, which is about 17.9 miles. In a straight line, we are exactly 10 kilometers from our landing site up here at Bradbury Landing, about 6.2 miles. But we've been like a dog going for a walk on a leash. We've meandered to the left and right a little bit, and so the dog has gone far further than its owner on this walk. But we've covered about 17, 18 miles, but we're about 6 miles from our landing site. And I'm going to split this part into two halves. One is the top half. So this is where we were 2.5 years ago. On top of this funny little shelf of rock here that's called the Green Hue Pediment. And that first Friday, from being remote, we did a drill right on the edge of that pediment that's called the Edinburgh drill hole right here. It was one of the drill holes in Ken's picture of all of the different drill holes that we've done. And since then, we drove off the pediment, we headed out across the floor here. And this whole area here is the kind of clay-bearing unit behind Vera Rubin Ridge that was in one of Ken's slides. This clay-bearing unit here is kind of where we think the best chances are for preserved evidence of a habitable environment. And so we knew that we were going to leave this clay-bearing unit and move on to kind of this clay-sulfate transition. And in doing so, leaving behind our best last good chance to throw everything we've got at this ancient habitable environment. And that's what we did right here, this location right here. Here's the, of course, traditional selfie from this location. What's unique about this particular drill site is that we actually drilled it 3 times. We drilled it once here, and for a third time right here. And we did that because we actually can do multiple things with the SAM instrument on board the rover. SAM lives under these 2 inlet covers right here. And it has multiple things it can do. It can run different kinds of mass spectroscopy by baking the samples and then measuring what gets vaporized from those samples. But we also have 2 different kinds of wet chemistry lab as well, but we've only got 2 of one kind of wet chemistry and 6 of another kind of wet chemistry. And so we saved them for a special day. This was that special day. We actually ran these samples through the SAM instrument 3 times. Once for a normal SAM analysis, once with one kind of wet chemistry, and once with that very special kind of 2 shots only of wet chemistry. Now, it takes a very long time for the SAM team to figure out exactly what their measurements mean. Yes, they detected organics here as well, probably their strongest organics measurement to date. But the analysis and the full deep dive of exactly what the SAM instrument's trying to tell us about what is locked up in these rocks is still to come. So we headed out from the clay-bearing unit and started heading from the clay-bearing unit to the sulfate unit. Now, this clay-sulfate transition is kind of a story of going from a warm, wet, ancient, habitable environment to the more acidic, perhaps drier environments that we see today. And you can almost see it just in false color pictures like this. If you look up here, those rocky outcrops there are very much a kind of a light beige, tan kind of color, like a mild gray color almost. And as we traverse south here, you can see the things begin to get pinker and orangier until you get to these layered outcrops down here. And just south of us from where we are right now, it is from orbit, is clearly purely sulfate-rich outcrops. The clays are gone, the sulfates are here. And so the story of the past 2 years has been this transition from that ancient habitable environment of a clay-bearing region into the drier, more modern Mars that is sulfate-rich. Now, we did take a trip through this patch here called Mariah Gordon Notch. I'm going to show you a picture of that. We wanted to go out to this ridge down here. This is an inverted river channel. Billions of years ago, a river flowed through here, and in doing so, deposited rocks that were erosionally resistant. And so, preferentially, everything around that old riverbed has eroded away, leaving this kind of inverted river channel. That's called the Geddes Vallis Ridge. We wanted to try and get out there and back again. But when we tried to climb up the green hue pediment and head our way across here, we very quickly realized it was going to take a very, very long time and do a lot of damage to the rover if we tried to make it all the way across. These ridges that you see here are kind of tens of meters across. And I have a photo that shows you exactly why you wouldn't even want to walk across this terrain, let alone try and drive across it. So we then turned tail, we headed back off the pediment, and we carried up through here to find ourselves where we are right now, which is just on the other side of another kind of pretty narrow canyon that I'm going to talk about in detail as well. This is right up in that little notch, Mariah Gordon Notch. This is looking down across the floor of Gale Crater. That distant rim of Gale Crater there is about 25 miles away to the northwest of where you're looking at here. The landing site is about 6 miles away. And you may notice that we're looking at a big shadow right here because this is as close as we got to the outcrop at Mariah Gordon Notch. And this caused something that we hadn't really thought of before. We'd always had difficulty driving around in terms of getting over rocks or dodging sand dunes and stuff like that. We've never had the larger scale terrain, cliffs, hills, outcrops, etc., be a kind of an active participant in the challenges of where we go and how we do our job. Some of you, I'm sure all of you, have at some point used like Heavens Above or something else to see when the space station is going to be flying over. Or you went to look for iridium flares back in the day. If you think about how often you've looked at the space station and where the space station was when you did that, typically it's going to be 20, 30, 40 degrees above the horizon, okay? Those passes where the space station is 70, 80, I saw one a few months ago that was like 89 degrees elevation. It was right overhead, right? Those are much, much rarer. And it's simply a function of where you can see and the distribution of those passes above you. The same thing happens to us with our Mars orbiters. So we have Mars Odyssey, we have the Mars Reconnaissance Orbiter, we have MAVEN, and we have the European Trace Gas Orbiter. That's how we get our data home. And they too have a distribution on where they appear in our sky. Very rarely are they straight overhead. More typically, they are 20, 30, 40 degrees above the horizon. Believe it or not, this hill here reaches 42 degrees above the horizon. And we had a scheduled communications pass with the European Trace Gas Orbiter that was completely occluded by this cliff. The orbiter never heard us. We never heard from the orbiter. We had an entire pass that was missing because of this cliff. That was the first time this had happened on the mission, and it's something we've had to work very closely to try and manage or predict or work around basically ever since. This is the green hue pediment. This is the area where we decided we didn't really want to walk across it. It may seem fairly benign in a view like this, but we had one of our geologists look at this closely and say that he wouldn't even want to try and walk across here because he would probably turn an ankle doing so. It's very hard to see when it's all foreshortened as you're looking out across the pediment like this. But these are the kind of tens of meter scale ridges that you saw in that orbital image. And these rocks are ventifacts. They are sharpened by the wind and would be incredibly damaging to the rover if we tried to traverse all the way across to the Geddes Vallis Ridge here. So we got as far as we were comfortable in doing. We essentially wallpapered the Geddes Vallis Ridge with as many kind of zoomed in photos as we could before doing a 180 and heading back off the green hue pediment. So we headed back into the valley, just to the east of the pediment, and then we started heading south. This was just a couple of weeks ago, and I talked about the kind of the next little canyon we had to try and get our way through, and that is this canyon right here. You've got a hill from this rover view to the left, that is to our east, and this hill here, which is to the rover's right, which is to our west. And if you look right in the middle here, you might just be able to see there are some sand dunes here. Now, remember I told you to remember the little black dot in that image that Ken showed? That is this rock right here, okay? Seen from about 4 miles away, we could see that rock from 5 years ago. Here it is right here. Believe it or not, that rock is 7 feet tall. It's actually slightly taller than the rover is. We actually went around the back of that rock before heading up through this little valley here It was extraordinary when we figured out that this one specific rock that we had jokingly said was probably about as big as the rover, and we can see it all the way from over here. We actually ended up driving right past that very same rock. So to explain some of the challenges we've got in getting through the more kind of crazy terrain that we're dealing with now, I thought I could explain the story of what we've been dealing with literally over the past 2 or 3 weeks. And it's this specific valley that's kind of been a point of some challenge over the past couple of weeks. Here is the orbital view. So if I go back to this view, you've got this hill on the left and this hill on the right. We're looking south, so this hill is to the east, this hill is to the west, okay? That was the hill to our left, that was the hill to our right. We are facing in this direction, looking through this valley. That rock from Ken's picture, there it is right there, okay? You can even see it from orbit, it's so big. Now, we wanted to get through here. If we can't make it through here, it's a significant diversion to find another way around, okay? It's like trying to get from one side of a city to the other. You either got to plow your way through and deal with the traffic, or you take the ring road and it takes an extra 20 minutes because of the traffic, right? There's no graceful way to get through here. Here are some of the constraints we had to deal with. Look at the sand dunes right in the middle. Those are kind of several meters across each. We're looking at an area here that's about 40 or so meters, maybe 120 feet across, 400 or 500 feet long. This is kind of the area of concern. Those sand dunes, consider them to be unpassable. There is a statistically likely chance that we could get the rover stuck in sand dunes of that nature and not get it out. And that's a bad thing to do with a $2.4 billion Mars rover. We try to avoid breaking it and avoid getting it stuck somewhere. The next concern is speaking to the Earth. So we send commands to the rover every morning directly from the Deep Space Network using antenna in Goldstone down here in California, in Madrid, Spain, and Canberra, Australia. And we do it in the rover's early morning. Basically, we let the rover wake up, have a cup of coffee, then we send it its email of what to do for the day from the Deep Space Network directly. And the Earth at this time of year is low in the eastern horizon when that happens. It's about 20 degrees above the eastern horizon. Well, guess what's in the way of the eastern horizon? It's that hill right there. And so we made a map of where could you not see the Earth from at the time we're due to speak to the rover, and it's this whole zone right here. And so if we drove, we could have said to the rover from that big rock, we could have said, hey, drive 20, 30 meters to the southeast. We could have parked the rover in there, and the next day it would not have heard from us because there's a mountain in the way. And we'd have had to use some cunning tricks to command the rover via other means that would have played havoc with our kind of planning cadence and our regular planning schedule. We don't get the data back to Earth directly through the rover direct down to the orbiter. Sorry, from the rover directly to the Earth. As I mentioned, as we went through that canyon a few months ago, we talked to the fleet of Mars orbiters that are doing good science the rest of the time. But when they fly overhead with us, we burst data up to them for 10, 15 minutes, and then they forward that data on to the Earth. So we use them as kind of relay satellites, as communication satellites. Well, those passes that can be low to the east or the west that kind of dominate the spread of where those passes are, well, any pass to the east, we wouldn't be able to see it from here. Any pass to the west, we wouldn't be able to see it from here. And now you can see you've got an over-constrained, essentially unsolvable problem. And what we did was pick what we were originally going to go down the eastern route until we realized we were having this Earth occlusion issue. We swapped it going down the west side here. And to give you a sense of what that view is like, I'm going to show you the view from right here, just before this little rocky outcrop right here. That view looks like this. And we did drop some communication passes to our west, some low westerly passes. We just knew they were not going to happen. And we tried to park the rover in such a way whereby when it was a communications pass we desperately needed to plan the next planning shift, we would kind of shift which passes we were using as our decisional pass. What pass are we going to use to decide what we're going to do next? And essentially write off a communications pass as that's likely to be behind the hill. We're likely not to see anything. So this was essentially the southwest corner of that little valley that we're exactly at this spot right here. And we have since successfully dismounted the valley. We've headed out towards the south here. And to bring things up to date, I'll show you the most recent images we've got at the end of my slide deck. Meanwhile, we have an entire environmental science team who've been looking not down at the rocks, but up at the sky. This is one thing we do on an almost daily basis is we take dust devil movies. We don't know where there are going to be little baby Martian tornadoes. We have no idea where they're going to be. These are fishing expeditions when we sequence movies like this. We pick a heading that looks like it might be productive, and we have a go and see what happens. And this is one of the best dust devils that we've seen. That dust devil in the distance there is about a half mile away. That this movie is taking place over a period of about 10 minutes, and it's about 40 meters across and a couple of 100 meters tall. And the most enhanced version of this, it actually runs off the top of the image. So we're looking at quite a sizable dust devil here. The irony being, if you were to stand in front of it, you wouldn't even feel it. Just be a gentle breeze as it blew past, because the Martian atmosphere is so incredibly thin. But we see these when it's local summer. Not very often, but we do see dust devils from time to time. This is one of my favorite observations. I was involved in designing this observation a few years ago. It's a paired observation. One of these was taken straight before the other. And what you're seeing here is a movie of 8 images, where what we've done is take each individual image and essentially just highlight the difference between each individual image and the full stack of 8 images. So it's kind of a mean subtraction attempt to really extract anything that's changing in these images. So look on the left, what you've got is some clouds up in the sky. You can see them moving. They're definitely moving up in the sky. There's something going on. But look at the ground. There are these dark bands marching across the surface. That is actually the shadow of those clouds projected onto Mount Sharp, the giant mountain we've been driving towards for 10 years. And so by looking at where those shadows are, you can figure out the speed and direction of these clouds. If you then take those same cameras, that same sequence, and point straight up at the clouds, well, now you can see their angular velocity, how fast do they appear to be moving in terms of degrees per second. And by knowing their ground speed and the angular speed, you can figure out the altitude of these clouds. And so by taking these 2 different movies here, what we are doing is taking a high altitude wind measurement. And these winds are tens of kilometers per hour. It's actually really quite fast wind speeds. And typically speaking, about 50 kilometers above the surface. We are talking about pretty high altitude clouds. Some seasons they tend to be water ice clouds. Some seasons, especially in the depths of winter, they tend to be CO2 ice clouds instead. This is one of my favorite images of the whole mission. Not quite my favorite. I am going to show you that one, but this is one of my favorites. This was a sequence I did with one of our science team members, a guy called Mark Lemon, who's been studying clouds on Mars for 25 plus years. This is taken after sunset. We're actually near Mont Mercou, the cliff right on the very right-hand end of that little sojourn we've taken over the past 2.5 years. We're looking up over a period of about 10 minutes, and that black band you see marching from left to right, you see it going here, 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 here. That is the shadow of Mars being projected up against these clouds above us. These are technically noctilucent clouds, or nacreous clouds, call them what you will. And again, by using the basic geometry of where is that shadow and what time were these pictures taken, we can figure out their altitude, and thus we can figure out how big they are and how fast they're moving. These are very high altitude. We're talking 50, 60, 70 kilometer high CO2 ice clouds at this point. It's quite extraordinary. And then just for fun, this is something we did last Thanksgiving. At about the same time we were approaching that little cliff channel called Mariah Gordon Notch, our project scientist said that the view looking out across the floor of Gale Crater was particularly spectacular. As someone who took those pictures, I happen to agree with him vehemently. And he said, can we take it again, but kind of at a different time of day or something? Or can we take it uncompressed as like a little postcard? I'm like, Ashwin, I'd be delighted to take that postcard again. And so I sequenced a 6-frame mosaic of our black and white NavCam images here. But I said, I've got one requirement, is that I get to take it twice. I want to take it at about 8 o'clock in the morning, and I want to get to take it at about 4 o'clock in the afternoon. Okay, so this is the exact same set of commands running twice, once in the morning and once in the afternoon, designed intentionally to generate this picture, which is a merge of those two. This is not a color picture. This is simply taking the morning images and applying them to kind of a blue color, and the afternoon images and applying them to this more orange color. It's a particularly beautiful result of just taking these 2 individual black and white images. You can see here, this is the afternoon. The sun is setting off to our left, which is setting in the west here. Rising east, setting in the west. Yes, setting in the west, because this is north. We've been heading south so long, you kind of get left and right and east and west confused. But you can see that the slopes to our right-hand side here are kind of sun-baked, and so they turn into the orange, and then the stuff on the left, which was illuminated in the early morning, comes out blue. I intentionally picked these colors to try and capture this. Mars is the red planet, but it's always very, very cold. A lot of our pictures, a lot of people say, It just looks like the American Southwest. And they're right. It's the same geological processes forming the same kind of landforms. Of course, it looks like places like the Badlands, et cetera, or the high desert of California, or Death Valley, or whatever. But those places are all, typically speaking, incredibly hot, and Mars is incredibly cold, as Ken had in that slide comparing Earth and Mars. And so this image was kind of trying to redress that balance of, yes, this looks like a nice warm desert, but it's actually a freezing cold place to explore. So what's next? Well, this is where we are right now. We've just come through this canyon. We're actually on these sand dunes right here, and we're going to carry on up the mountain. Those very bright rocks out in the distance that Ken talked about are way up here. We're going to be heading through to this strange geological unit here. You can see this dark patch that runs all the way around these hills here. That is what we call the marker unit. It's an interesting geological unit. We're going to try and drill somewhere in here over the next couple of months. And then we're going to keep heading up the back of this Geddes Vallis Ridge, up this river channel, take a U-turn, and then we're going to head across slope. We can't really go much further than this because of what the terrain is like. Then we're going to start going across slope. And way out over here, there is some incredibly strange terrain. It's called boxwork terrain. We think most of this was laid down in the absence of water. We think we're leaving behind the ancient habitable, warmer and wetter story of Mars. And we think by the time you get up here, this is more like the early Opportunity mission, which was more like White Sands, New Mexico than kind of hot springs or anything like that. But this boxwork structure speaks to kind of aqueous activity after those rocks were laid down. So what's that story about? That's probably where we'll get to over the next 3 years. It's everything you see in this picture. And that's what we're currently funded for. We got our next mission extension starts at the end of September and is for another 3 years of exploration. And we expect the rover to be in fighting fit form to keep going even after that, given the opportunity to do so. Finally, I'm going to show you the most recent pictures we've got. If you go to the raw image webpage, and I'm going to drop links to that at the end here, this was the most recent microscopic imager picture we took. This looks a little strange because at the time the rover was actually straddled one of those sand dunes coming out from the other side of this valley. This was taken at 3:15 East Coast time on Thursday morning. And to bring it bang up to date, when we came into work this morning, this was the view that welcomed us. And so this is that little sand dune. You can see we've backed away from it. We've turned the rover around a bit to try and dodge around the worst of this sand dune. And we're now going to head out through this valley to then try and get to the marker unit. And the marker unit is actually right here. It's that kind of unconformity in this hill here. That right there is that flat dark feature in the orbital imagery. That's our next goal. And so come Sunday evening, the rover is going to be heading out in this direction. And we'll come in on Monday and keep plodding our way up towards the marker unit. These images were taken at 5:15 this morning, your time. All of these pictures that I'm showing you are available for anyone to see anywhere in the world. We share what we do in as many ways as we possibly can, very much a legacy of how Spirit and Opportunity did their stuff. So all of the individual raw images that we take go online the second they reach the ground. When I get up in the morning, I don't need to VPN into work to see what the rover's been up to. I literally grab my cell phone, I look at the Mars website, and I can see the raw images right there, just like you could, because this is your mission just as much as it is ours. And so the same pipelines that take the downloaded data and process it into all the calibrated stuff that we need to do our job, takes those images, stretches them to make them kind of make sense to just a normal JPEG, and throw those online as well. Every time we've driven, we also take a 360-degree black and white panorama. Those also go public as well. We have a pipeline that kicks off. It looks like the rover is driven. I got all these pictures. I'll assemble them into a mosaic. I'm going to throw that on the repository for the science team and throw the PNG on the public website as well. Once our geospatial experts, our keeper of the maps, Fred Califf or Tim Parker, have updated the exact location of the rover, that data goes public as well. And we have a portal that looks a little bit like Google Earth, but it's for Mars. That's where I got those screenshots of our route, is from this public webpage. It's Where is Curiosity. You can zoom in and out just like Google Maps, and you can see where the rover is right now. For the more polished, beautified kind of press release images, go to the JPL Photojournal. It's a superb portal. You can search by planet, you can search by mission, you can search by instrument. It's a great place to go and get kind of the best published versions of an awful lot of our data. Every time we have a tactical planning shift, either a member of the engineering team or the science team writes a short blog update on exactly what we're planning to do that day. Those go public as well. And finally, all of the data that we take, every spectra, every wind measurement, weather measurement, SAM measurement, ChemIn, Mastcam, RAD, REN, REMS, DAN, all of the different instruments on board the vehicle, all of their data ends up in the public domain through what's known as NASA's Planetary Data System, the PDS. And the best way to get a hold of all of the Curiosity data is through what's known as the MSL Analyst's Notebook. If you just Google for Analyst Notebook Mars, you'll find this portal. And for that portal, you can find every single image we've ever taken, every spectrum we've done, every laser shot, every SAM measurement, ChemIn, all of our instruments, all of the data ends up there for anyone in the world to take a look at. And with that, I think I'll hand it back over to Ken.
Ken, you're muted.
Sorry. I was going to talk more about the educational resources, and then I realized that's the talk I gave in April. So I don't want to, bring that up again. I would suggest if you want to get our the resources to go back to April's presentation, which I did. So does anybody have any questions out there for anybody?
We've got a question in the room.
Hi, thank you for your talk. A question I have is, do you know, and this may be a question for both of you guys, how much has the instrumentation sensitivity changed from the first, when it first landed to now? Because I would imagine things have changed in how you interpret the data.
Yeah, we are not a fresh spring rover anymore. Remarkably, most of our instrumentation is pretty much as fit for purpose as it was the day we landed. Some stuff has certainly degraded. The DAN instrument, the Dynamic Albedo of Neutrons instrument, which is looking for hydrogen abundance in the soil, it has an active portion and a passive portion. The active portion is significantly weaker than it was when we landed. It's 10 times past its design life already, and it's still just about trickling out an active neutron source to measure the albedo of neutrons beneath the rover. But it's significantly weaker. But what they do is simply stack the data we get from one particular location, or just rely on cosmic rays to produce those neutrons for them to measure. And so they're still getting good data despite not being quite as strong as they used to be. The SAM and the ChemIn instruments, the big laboratories inside the rover, they both have a finite number of sample holding vessels. SAM is a series of small cups. ChemIn is a wheel with a series of little cells for doing its analysis. And we're through about 2/3 to 3/4 of all of those in both instruments. But in both cases, they have sufficiently characterized what is in them enough such that we can throw another sample on top, analyze that, and essentially subtract out any residual nonsense from a previous sample. And so we have some pristine cells in both for kind of high priority, really cool science, and we'll save those for kind of the next best things that we find. The cameras are getting a little old. They're getting a little dusty. They are all still working great. The rover itself is looking a little weather worn. We're a little filthy. But truthfully, that doesn't really matter. The wheels are beaten up to heck. But we think they're good for probably another 20 plus kilometers of driving. And we're going to run out of good science by then anyway. And this segues into a question we got through chat, which is there an estimate of the remaining life of Curiosity? So we're RTG powered, just like the Voyager or Pioneer or the early Viking landers or New Horizons. We landed with something around 100 watts coming from our RTG. What people think like the rover just drives off the RTG. When we're awake, we're actually using more power than the RTG can provide. And so the rover spends the vast majority of its time napping. And then when it's napping, it's being trickle charged off the RTG. When we wake up, we use a chemical battery inside the rover. And we are typically awake for 4 to 8 hours per Martian day. And early on in the mission, you model everything incredibly conservatively. Like, how much power does it take to do X, Y, or Z? And you overestimate massively because you don't want to brown out the rover. 10 years in, our ability to model our activities in advance is significantly more accurate. And so largely speaking, the cadence of our scientific productivity has not dropped as our RTG output has followed its kind of half-life decay. What's happened is, as it's decayed, we've swallowed that difference with increasing accuracy of our power modeling, but we are about to cross that line whereby we will be reducing the cadence of what we do with the rover thanks to the degrading RTG. What we can do with that is go to NASA and say, hey, we're not going to be able to do 3 or 4 planning shifts a week. What we're going to do is say, you know what? At 1 day in 3, just going to be a recharging day. So how about we just always do 3 shifts a week, or maybe it's 2 shifts a week. And so what we can do is, as the RTG degrades, we can ramp our budget to match. And so we only plan at a cadence that the RTG output can match, and in doing so, reduce our budget as time goes on. But we have a 3-year budget now that will take us through from this September. So let's call that 2023. So we basically have 2023, 24, and 25 on the books from a budget point of view. We fully expect to be able to successfully pitch for another 3 years beyond that. The review board for this mission extension, known as EM4, warned us to expect that the next extended mission might be our last, which would be EM5, that would take us from 2026, 27, 28. Many of us are pretty bullish that we might be able to keep the old goal going beyond then. We think we'll be able to come up with some creative ways to keep operating beyond then, perhaps another 3 years beyond that. I think it might be a little bullish to suggest that we're perhaps less than halfway through the mission, but I think we're probably about halfway done with the life of the vehicle. The SAM instrument may be done with empty cells, Chemin may be done with empty cells, the wheels may be beaten up to heck, but I think we'll still be able to drive around a bit, use the arm a bit, take some weather measurements, take some pictures. At least 5 years from now, maybe if we're lucky as much as 10. And there was one other question, which is, what happens when you reduce your workload? Do you do another mission in addition? Yes. So many of our team members are already shared with other projects. A lot of our team also work on the Perseverance team. I mentioned Taryn, our engineering camera team lead, who replaced me when I became the planning team chief. She works 50% Perseverance and 50% Curiosity. So she gets to take pictures with both rovers. In fact, she's the only person currently taking images with 2 rovers on the surface of Mars. The last person to do that was me when I worked on Curiosity and Opportunity at the same time as well. So people will roll off onto other projects. They'll work MSL part-time. Most of our team is already part-time doing something else at the same time. I think that covers everything in chat. Is there anything else in the room?
We have another question in the room. One moment.
On the last 2 slides that you showed, before you got to that one that said how to follow along, which shows 6 selections, how tall are those mountains above average terrain? How high? And they look pretty steep. And is the rover, like those right there you showed, is the rover able to climb up those?
So what we accidentally came up with this suspension system that we've been using for 25 years with little Sojourner, Spirit, Opportunity, Curiosity, what we've accidentally designed is a mountain goat. We can climb 32-degree slopes, and we have done successfully. We have parked on 28-degree slopes and done contact science with our robotic arm on slopes that high. We can climb slopes that, from a health and safety perspective, you would need to be have a harness and be roped into to work alongside the rover. And so, yeah, we couldn't, for example, head straight up this hill right here, because that is simply too steep. But we can navigate our way around this stuff. But you're looking at 45-degree slopes here on many of these higher buttes and hills around us here. But we can dodge our way around them, and what we can do is, instead of saying, you know what, we need to get to the top of this hill right here, what you do is you have your science team map out the geology of the layers in this rock and explain to you where you can go over here that might be the exact same layer, right? And so we've had Mother Nature take a nice slice through this stuff through erosion over time, and we simply find the most graceful way to access the layers that might otherwise be inaccessible due to kind of the crazy slopes that they're on. I hope that answers the question.
One more follow-up, I think.
But wonder how high above the ground they go up, such as in feet
Oh.
or meters.
Oh, so the two hills to our side right now, the ones we literally just drove through, I think the number is something like about 300 feet high. Those two hills here. The mountain that is still ahead of us, we are now about 1,800 feet above our landing site. That was, I've written, because it looks like I'm cheating. I am. I wrote the numbers down this morning. So 17.9 miles away is where we landed. We're now 6.2 miles from our landing site. We have climbed 1,800 feet in total from where we landed. Mount Sharp, the peak of the central of this mountain, of the central peak of the entire crater, is taller than Mount Whitney. It's like 15,000 feet. Right, in total. We're never going to make it to the summit of that. But the cool stuff around us is on the order of 100 to 400 feet kind of peaks here and there, and they make our traverse planning a nice challenge. It makes it very exciting. I saw another one in chat, which is, will the soil samples be sent back to Earth? So our samples are not going to get sent back to Earth, but our friends on the Perseverance project are collecting samples explicitly for that purpose. And if I turn around, do I have it here? I may have a 3D printed model, or it may be in the office, of one of Perseverance's sample collection tubes. No, I left them all in the office. So the Perseverance mission, it doesn't have the SAM instrument, it doesn't have the Chemin instrument. In other ways, it looks very similar to Curiosity, but what they've done with the front of the Perseverance rover is strip out all of that kind of analytical laboratory for in situ science and replace it with a sample processing and caching system. So what Perseverance does, instead of drilling a rock to collect a sample to deliver into a lab in the rover, it does a rock core and then seals that up in a metal tube. It's about this long. It's about the size of a decent sized cigar tube, okay, and looks not dissimilar as well. And what they do with that sample tube is cache them inside the rover. And Perseverance is probably only a couple of months away from then depositing a cache of those sample tubes on the ground in a nice clear patch of ground not far, about halfway between where it is now and where it landed. It's going to keep some samples on board. It's been collecting its samples in duplicate, and it's going to dump half of its good samples right there, keep the other half on board, keep on going, collect more samples as it heads up the delta of Jezero Crater, out of Jezero Crater altogether, and up onto the plains beyond, collecting samples along the way. About six years from now, we're going to have what's known as SRL, the Sample Return Lander. That's going to be sent to Mars. It will either land near where Perseverance is at the time, if Perseverance is still trucking along, or if Perseverance has failed for some reason at that time, it will land about where Perseverance is right now, and will use a couple of helicopters derived from the Ingenuity helicopter that Perseverance has. And those helicopters will just head out, they'll pick those samples up and return them to the lander. The lander has a big robotic arm that can pick those up and stick them on the top of what is essentially a small rocket. It's called the Mars Ascent Vehicle, the MAV. It's about 8 feet tall. It weighs about half a ton. In terms of kind of energy, it's about the same as a kind of air-to-air missile. You don't need a giant Atlas V to get back into space from the surface of Mars. This MAV is more than sufficient. It has a capsule on top that will be able to handle about 20 or 30 different samples, and so they will be cached on top of the rocket. The rocket will then be oriented for flight. It will launch back into orbit around Mars, where a European-built orbiter will rendezvous with it, pick up the top of the rocket, the kind of sample canister, put that into a sample return capsule, fly back to the Earth, and then drop that off, and it will land in Utah probably about 10 or 12 years from now. So a lot of the engineering subsystems of Perseverance were designed for Curiosity, and they're like taking lessons learned from us right now about how long have our motors lasted, how long are all our subsystems lasting, because if Perseverance is still trucking when the sample return lander actually makes it to Mars, the sample return lander will land near Perseverance. Perseverance will just drive up to it, drop the samples, back away, and then the lander can pick them all up, stick them in the rocket, and send them back on their way home. Another chat, I love this question. What was the reason for putting the Easter egg message on the Perseverance parachute? And, for example, the fact that if once every rotation, our wheels technically spell JPL in Morse code. Fun fact about that. When the Spirit and Opportunity landers landed, their wheels, their front wheels were tucked up like this, right in front of the rover. So if I'm the rover's front hazard cameras, the first thing that Spirit and Opportunity saw was its front suspension upside down and inside out, right in front of it like this. And what we'd done is put a JPL sticker that technically, once the rover was right side up, would have been upside down, but it said JPL right in front of the rover's eyes, right? And NASA headquarters were kind of like, guys, you really shouldn't, we're NASA, right? We're one big agency. We all work together. You can't go writing JPL and everything. And we're like, our bad. We didn't really think about it. It's fine. Anyway, fast forward 6 short years, and somebody notices that the flight wheels for Curiosity have this grouser pattern in their tread that has these holes in it. Those holes, that pattern is there for a reason. It's so that once every revolution, we leave a unique footprint behind that we can look at with our cameras if we want to see if we're getting much wheel slip, that kind of thing. Somebody noticed that those holes might perhaps accidentally spell JPL in Morse code because we're kind of bratish about that kind of thing. And same with the parachute. The parachute in particular was intentionally done as something cool for people to try and figure out. You could make that pattern anything you wanted. And it's nice to have a pattern of some kind because that helps you do 3D reconstruction of the parachute from the amazing cameras that filmed its deployment. But if you're going to make a pattern of some sort, why not make it a pattern that people can have fun with? So it's a little bratish on our behalf that we tend to kind of write our name on things or write JPL every pi times 50 centimeters, 1.5-ish meters on the surface of Mars. But it's fairly harmless fun, I think.
Any more questions in the room? And any more on the chat? No? All right, awesome. Thank you, Ken. Thank you, Doug, for this presentation and sharing the journey of curiosity of the last 10 years.
An absolute pleasure. Keep following along. We've got plenty more science and exploration to do.
Yes, we do. Yay.
Thanks,
Thanks, Doug.